Good evening. Thank you so much for coming. My name is Curtis McCulley. I'm an astronomer at Las Cumbres Observatory, and we are just delighted to have Dr. Alan Stern here to tell us a little bit about the New Horizons mission. So Las Cumbres Observatory is a network of robotic telescopes. We have 21 telescopes around the world, but it's all managed right here in Goleta. So, our speaker tonight, Dr. Alan Stern, has a pretty impressive resume. Now, what he doesn't know is we just had an astronomer from Las Cumbres Observatory go talk to his PhD advisor, and so he told us all kinds of stories about him. The only one I'll share is that when he got to graduate school to get his PhD, he walked into his advisor's office and said, "I'm going to get my PhD in 3 years." And everybody just laughed and said, "That's not possible." But he did. And so since then, he has been involved in many, many space missions. And for a while, in 2007, he was the NASA Associate Administrator for Science, which is essentially the top-ranking science officer in NASA. And under his tenure, there were a record 10 major new flight projects that were started. He's the mission leader of the New Horizons project, which is exploring the outer parts of the solar system. And so that's what he's going to tell us about tonight. So without any further ado, welcome, Dr. Stern.
I thought we'd make this a little bit more intimate, and I would sit, and we'd just talk, and then you can ask questions. It's a pleasure to be back in Santa Barbara, and it's a pleasure to be here tonight and tell you about a really amazing adventure, a space project called New Horizons that involved 2,500 men and women to design and build and fly that spacecraft, and it's design and build its rocket, fly it across the solar system, and conduct the farthest exploration in the history of our species. And I had the privilege of leading that project. Now I'm going to have the distinct privilege of having to figure out how to go from your slides to mine. Should we just hit escape? And then where on the desktop did you put mine? There we go. Super. There we go. Okay. So, and I think we were going to turn the lights down on me just a little bit so you could pay attention to all the good eye candy up there. What I'd like to do is start with a little background on the exploration of the solar system, which has been taking place now for over 50 years, since the beginning of the space age. And just before New Horizons flew past Pluto, which was kind of the anchor leg, if you will, in that relay to explore all the planets that were known at the birth of the space age. In the spring of 2015, I commissioned this video about the exploration of the planets. It just runs a couple of minutes, but I'd like to play it for you as background to what we did. Here we go.
It has been over 3,000 days since we left Earth. We're now almost 5 billion kilometers away from home. Out here, where the sun is distant and faint, is a place no one has ever seen before. Pluto and its system of moons, the farthest worlds ever to be explored by humankind. Since the beginning of history, the points of light in the sky have captivated us, particularly those special ones who mysteriously seem to wander. We call them planets. And upon learning that our planet is only one of many in our solar system, how could merely observing these points of light from home ever have been enough? Half a century ago, we began the exploration of all the planets. making ever more distant journeys. Each new world revealed its own startling complexity, character, and unimagined beauty. It has been a long wait since our visit to Neptune. But as we now approach the Pluto system, reaching farther again, our generation is about to complete the historic first era of planetary exploration. Who knows what wonders await us at these new horizons?
And 3 months later, we did that. Meet Pluto. This is a new type of planet. I'll have more to say about that. And really a scientific wonderland. I thought I'd tell you the whole story of how we came to do it and a little bit about what we found. But to tell that story, we have to start a long time ago. At the turn of the 20th century, with this man, Percival Lowell, from Massachusetts, who was a gentleman scientist and from a wealthy family who founded Lowell Observatory in Flagstaff, Arizona in the 1890s. And Lowell became convinced that beyond Uranus, discovered in the 18th century, and Neptune, discovered in the 19th century, there was another planet. He called it Planet X, orbiting out there even farther. He and quite a number of astronomers of the day thought that they saw evidence for that planet tugging on Uranus and Neptune, and from the orbital mechanics of it, they could calculate where to look for the planet that they wanted to hunt. Turns out, it took a long time. Lowell's search began in 1904, and he died in 1916, and they hadn't found it. He dropped dead of a stroke one November day, and his will left his fortune to the observatory and to continue the search for this Planet X. It was quite a lot longer. In 1929, that this man, 24-year-old Clyde Tombaugh, was hired to carry that search out. This was Clyde's first job. He was hired literally off of a Kansas farm. It's his first trip away from home. And he turned out to be a gem. He not only took over the observing, going out to the telescope at night and taking the data, but he figured out that the entire technique that they've been using for 25 years was going about it the wrong way. He reinvented the method for detecting moving targets in the deep outer solar system. He did all of the data reduction, and he did all of the data analysis, staring at images of the sky, sometimes with tens of thousands of stars in them, looking for a little faint moving dot, moving at just the rate that would indicate it was far away beyond Neptune's orbit. And of course, this was a big challenge because in the foreground, there are thousands of asteroids moving through the field of view, and comets, and there are variable stars and novae going off. Never once in the year that Tombaugh pioneered this search did he ever come to his boss with a false report. I found it. Never mind. But in January of 1930, barely a year after he arrived, he did find it. These two images on the left and right here are from those the very discovery images of Pluto made at the beginning of 1930. Now, I asked Clyde about this once. I met him in the 1990s, shortly before he died. And he said, oh, it wasn't that hard, you know. Pluto's, it's always marked by a, you know, it's got an arrow pointed at it. But it was really an amazing, amazing tour de force. So much so that no one discovered anything further out than Tombaugh until the end of the 20th century in the 1990s. He was basically 2 generations ahead of his time. It's an amazing story. Somebody should make a movie about Clyde Tombaugh because it's a great kid off the farm American success story, but I digress. This is a scan of a couple pages in a book about the planets from when I was a kid, growing up at the beginning of the space age. And I'm sure many of you saw diagrams like this as a kid. If you grew up when I did at the beginning of the space age, a lot of them had tables like this, where each column from left to right is another planet, and the rows represent features that were known or not known about it, like the surface composition and the number of moons and the temperature of the surface, and so forth and so on. And I just want you to look all the way to the right. Pluto's the last one, of course, but it's the one with all the question marks, because we didn't know a thing about it. The technology of the middle 20th century, even 30 years and 40 years after Tombaugh discovered it, was too primitive to learn very much. But as our technology got better in the 80s and the 90s, we started to understand what a fascinating place Pluto really is. The top diagram here is called the spectrum. It's a plot of the intensity of light as a function of its wavelength, which is what's plotted horizontally. And I show you this squiggly line plot only to say that by the last bits of the 20th century, we were able to get spectra like this one, obtained in the early 90s, of light reflecting off Pluto's surface and returning to our telescopes here on Earth, that showed us that the surface composition was full of exotic ices like carbon monoxide and methane, that's condensed natural gas, and nitrogen, that as a physicist you would recognize from knowing the properties of these materials would conspire to make a very complex interaction. You know, we have water ice here on the Earth that can move around. It can snow in some places and rain in others and evaporate. All 3 of these ices on Pluto's surface can move around. It's a very complex environment compared to, for example, the Earth and Mars. On the lower left, you see a plot of the intensity of starlight of a star that was observed in 1988 to pass behind Pluto. And it was observed by 8 ground-based telescopes and a NASA airborne observatory to search for evidence of an atmosphere around Pluto. And in fact, that's exactly what was found. The gradual diminution of that light fading out over about a minute and then reappearing and coming back to full strength over about another minute is a direct signature of atmospheric refraction, proving that Pluto had an atmosphere. And if you look closely at this graph, you'll notice that the light kind of falls at a gentle pace and then it steepens up towards the bottom here, steep on the exit, and then it's gentle again. That's telling us that there's structure in that atmosphere, structure with altitude, that's changing the index of refraction. It could be a temperature effect. It could be due to hazes. Back then we didn't know. But the fact that Pluto had a complex surface composition and an atmosphere already attracted a lot of scientific attention. In the late 1970s, Pluto was discovered to have a giant moon, half its own size, about the size of the state of Texas. It's called Charon. And from everything we could learn about the satellite and the planet, it became obvious that the only way for that particular satellite to have been formed was through a giant impact of another small planet striking Pluto and spalling material off into orbit around Pluto, where it would condense into a satellite. Now, the interesting thing about that, to those of us in the planetary science community, is that's exactly how the Earth-Moon system was formed. And nowhere else in the solar system except at Pluto did we find another example of this so-called giant impact mechanism for forming a satellite. So we also knew, even in the 80s, that Pluto had a lot to teach us about the formation of the Earth-Moon system, because it's the only other extant example of this formation mechanism that was known. And then, this was one of the greatest surprises, because we knew Pluto was out there on the icy edge of the planetary system. It's covered in these exotic ices like nitrogen and carbon monoxide and methane that I told you about. Its surface temperature is about 40 degrees above absolute zero, so we all expected an icy planet. Except when we could get its size and its mass and derive its density, we found out that Pluto's actually a rocky planet. That from its density, shown here in this little model, it's mostly a big rocky core with an icy shell. So you know, your mom used to say, don't judge a book by its cover. Don't judge a planet by its cover either. So this was one of those who ordered that moments. How could something formed in the outer solar system be so rocky? Well, all these different tidbits of information about Pluto's satellite formation, its atmosphere, its surface composition, its interior, attracted a lot of interest to the study of this very distant world. But we were still greatly limited by technology. This is the best picture of Pluto ever made before New Horizons. Every time I show this picture, people laugh. And that has a special meaning to me because I took this picture. I was the principal investigator of this program, and it's using the biggest, baddest gun we have. This was made with the Hubble Space Telescope. But because Pluto's so far away, this is all you get to see. Now, truth is, we wrote papers in the refereed scientific literature about this image. We overinterpreted this for 4 or 5 papers in a row. Don't you see the northern polar cap? You know, you just, as a planetary scientist, you need to do better than this. Let me show you this image. This is the kind of resolution you need on a planet to make heads and tails out of what's going on. But even with a Hubble, we couldn't get anything like this with Pluto. Let me illustrate my point. I asked Amanda Zangari, who's one of my postdocs, the first day that she arrived from MIT, would you take this image of the Earth so that I can use it in public talks and pixelate it to the same resolution as the best image of Pluto? And she did. Now, what could you learn about the Earth from this image? Not much. It's hopeless. You can't even tell there are continents and oceans, the most basic facts. I'll drive that point home a little harder. Who wants to guess? Mars. Oh, that was Julian that said Mars. Close. Not at all. You can't tell at that resolution what's going on, and that's why we send missions to the planets, because we have to get up close to have the resolution to really be able to tell. And so, you know, in the 60s and 70s, as that video indicated, we started exploring with very simple pioneering spacecraft to the closer planets like Venus and Mars. And by the 1970s, we were doing a little better, and we're branching out and sent a program called Voyager, Voyagers 1 and 2, out to visit the giant planets of the solar system, Jupiter, Saturn, Uranus, and Neptune. And the Voyager mission actually had an opportunity to fly on to Pluto, but decided not to do it because they wanted to study some aspects of the Saturn system that precluded, by taking that route through the Saturn system and studying its moons, also going to Pluto. So about the time that Voyager finished its work in 1989 with this flyby of Neptune, several of us who were graduate students and postdocs and young professors got together and said, you know, we really ought to go to NASA and see about flying a mission to Pluto. Voyager's not going that way. The only way we're going to do this, it's fascinating. We know all these fascinating aspects of it. We're never really going to make progress unless we send a mission there. Surprisingly, I got drafted to go see the head of planetary exploration at NASA. I was still a graduate student. And it was May of 1989. And I went and saw this gentleman, Jeff Briggs. And I asked him, why don't we study having a mission to Pluto now that Voyager's finishing at Neptune? He said, well, that's a great idea. No one's ever brought that to us before. I was astounded. And he said, let's do that. And so he started a study group. And I thought, man, this is just too easy. And I was right. Over the next dozen years, we were trapped in a maze in which we studied 6 different kinds of Pluto missions, from houseboats to hamsters. Every possible incarnation of how you might do this, and not a one of them got off the drawing board. 14 years wandering around the Washington Beltway trying to find $1 billion. And you don't do that very easily because it turns out that there are dozens of good ideas all the time for things that NASA should do with its limited budget to explore the solar system. And it can't just be first come, first serve, or maybe who knows who. The process that we have is actually a process that vets all the ideas through the National Academy of Sciences, which once every 10 years conducts something called a decadal survey and basically ranks sometimes as many as 100 proposals to find the cream at the top for the few things we can afford to do. And you have to not only be on the A list, you have to be at the top of the A list to get funded, because typically NASA can only afford to start a handful of missions out of 100 that might be proposed. What made the difference for the exploration of Pluto was not any of the things that I told you about a fascinating atmosphere, rocky planet, such a puzzle on the outer edge of the solar system, this fascinating formation mechanism like the Earth-Moon system for Pluto and its moons, surface composition, all that was good. That'll get you on the A list, not to the top. What made the difference was a revolution that took place in my field, in planetary science, in the 1990s. Remember I said that it took 2 generations after Tombaugh before anything was discovered further out? All that while, across the 30s and 40s and 50s and 60s and 70s and even the 80s, when kids learned about astronomy in grade school, and they learned a little something about the solar system, they saw diagrams like this. This is a map, if you will, of our solar system as we understood it in the 20th century. And here's the architecture. I'm sure you were taught this, but let me refresh your memory. On the inside, down by the sun, there are 4 closely packed planets called terrestrial planets. They're all each rocky. They're each roughly, kind of half or a third of the Earth size up to the Earth's the biggest. And they all orbit in close. They're called the terrestrial planets: Mercury, Venus, Earth, and Mars, in that order. And then they're surrounded by a debris belt called the asteroid belt. And then much further out are the orbits of 4 giant planets. And these are giants. Jupiter has a mass more than 300 times the mass of the Earth. And Saturn's about 100 times more. And they're on vastly bigger expanded orbits. And then beyond all 8 of those was Pluto, which didn't fit either pattern, which orbited in kind of a crazy orbit by comparison, and which is very small. It's like the size of the United States. It's not a terrestrial planet. It's not a giant planet, just a misfit. Now, how many of you watch CSI? Right? When they find the 1 drop of blood, it probably means there was more, right? It's always a clue, right? And Pluto was, in effect, a forensic clue that Tombaugh discovered, but no one knew how to interpret it. But then, beginning in the 1990s, we started to make discoveries of other objects out there beyond Neptune. And Brad, if we could turn this one down a little, I'm going to talk over it. So now we're looking down on the orbits of the giant planets, those 4 circles, and all these dots that are appearing are discoveries made in the 90s of other objects, Pluto's cohort orbiting out there with it. The ones that are bigger dots are bigger worlds. Some of them are about, but somewhat smaller than Pluto. This is the revolution that I spoke about. It's the discovery of the 3rd zone of our solar system. Beyond the terrestrial planets, beyond the giant planets, was the Kuiper Belt. This structure, the largest structure in our planetary system, and we didn't know about it until the 90s. Tombaugh's discovery in 1930 was a hint, a clue. He found the biggest and brightest object there, but nobody found anything else until much later. Turns out, this completely revolutionized our field. First of all, the solar system map that we all learned about in grade school was completely wrong. It's not what we thought were the outer planets. Were really the middle is really the middle zone of the solar system. The 3rd zone, it's as if we had maps of the world, the Earth, until the 90s that were missing the largest structure, the Pacific Basin, Pacific Ocean. And then it not only revolutionized our knowledge of the architecture, but also the population content. We learned there was a 3rd class of planet, the so-called dwarf planets, that outnumber the terrestrial planets and the giant planets combined. All of these objects shown here are real planets on the outer edge of our solar system. They're shown to scale. Pluto's the largest, Many of them have moons. They come in different colors. They have different surface compositions and interior structures and densities, and some have atmospheres and some do not, and so forth and so on. This is a very rich population. Now, who's the misfit now? There are more of these guys than the giant planets and terrestrial planets combined. In fact, I love this little diagram because, you know, the solar system was really good at making planets. It just that it mostly made little ones. Across the top are all the planets of the solar system: Jupiter, Saturn, Uranus, Neptune, Earth, Venus, down and down in order of size. Pluto is not the smallest at all. That's Pluto right there in the middle of the distribution. All these little ones were discovered later. And this discovery of the third zone of our solar system and the third class of planets in our solar system so shook my field that the National Academy ranked the exploration of Pluto #1 on the runway in 2003 in that decadal survey. Because by studying the Pluto system, we could not just learn about Pluto and its moons, but by inference about this whole new region of the solar system and this whole new class of small planets. So it went right to the top of the priority queue. That's the decadal survey recommendation: highest funding priority, a medium-scale mission, new start, to explore Pluto in the Kuiper Belt. And then NASA called for proposals. 5 industrial teams formed. I got asked to lead one of those teams. We called our proposal New Horizons. That's the cover of that proposal. It's about as thick as an old New York City phone book, filled with spacecraft designs and instrument designs and cost plans and management plans and education and public outreach and everything else you can think of. As I said, 5 teams competed. We were lucky enough to win. And we came out of that competition in November of 2001. The winners selected to fly the first mission out across the solar system to the Kuiper Belt and to study the Pluto system. And I have to tell you, what we signed up for was kind of a tall order. What NASA offered to do this, they were looking for a breakthrough. They said, we need you to do this in half the time that anybody's ever done an outer planets mission. And we only have 20% of the budget that Voyager had. So, you know, you often hear at work, you can have faster or cheaper, but not both. This was one of those. We signed up for both. A real cost breakthrough, 5 times less money, and do it in half the time. And so, as I said, 2,500 people worked on this project, and this is an unsung group of Americans. They worked nights and weekends for 4 years flat, from 2002 to 2005, to design and build and test this spacecraft and get its rocket ready and get it out there to launch, because we only had one launch window in January of 2006, lasting 3 weeks long, and if you miss that, you come back in 10 years, the next time Jupiter's in position. So as I said, they signed up for a lot of work. All of us did. My daughter Sarah was in high school then, and I was home on the weekends, but she tells stories about things that happened in high school. I don't remember any of that. Right before we launched, I asked my secretary, my assistant, Jeanette Thorne, hey, would you add up how many trips I took on New Horizons during those 4 years? She said 232. And I was just one of all these people that were working on this. You never heard about us. It's a great story, and so, in an unabashed plug, David Grinspoon and I have a book coming out next year, and you can order it this Christmas on Amazon, pre-order it. It's called Chasing New Horizons. It tells the whole story. There's some dirty politics in it. There's some technological challenges. There's some amazing things that happened. There's some luck. And it's the whole flight mission all the way to Pluto, in addition to how this all came to be. This is the spacecraft that we built. It's one of my favorite pictures of New Horizons because there are all these people around it, and you can see how small it is. If you ever go to Washington, D.C. and visit the National Air and Space Museum, there's a hall of planetary exploration, and Voyager's hanging in the hall, and it's big. It stretches 50 feet tip to tip, counting the antennas. Little New Horizons is next to it. But, you know, you can't, like I said, you can't judge a book by its cover. You can't tell how good New Horizons is by its size. You know, Voyager was built in the 70s, when computers would fill a whole room, have blinking lights, and cost millions of dollars, and had very little firepower. Well, just like the computer revolution between the 70s and the 2000s took us from mainframes that cost millions and did almost nothing, right, to laptops and tablets that are tiny in comparison, and they only cost hundreds or thousands of dollars. Nothing by comparison. And yet they have more power, orders of magnitude more power. The analogy is a good one. Voyager to New Horizons, same thing. New Horizons is much smaller but much more powerful, and it cost a lot less. Here you can see some of the main aspects of the spacecraft. That's the dish antenna that we use to communicate back with the Earth. This box contains all the subsystems to do the entire flight mission. The propulsion system, the thermal control system, the guidance system, the main computer. Everything is twinned inside. There's 2 of everything, so that if something breaks, we have a backup. The scientific instruments, like these 2, are mounted on the outside. There are a total of 7. I'll say a little more about that in a minute. Because the spacecraft is going so far from the sun that sunlight is 1,000 times weaker than at the Earth, we have to power it with a nuclear power generator. I know it looks like a hair curler. It's not. That device, called a radioisotope thermoelectric generator, is fueled by plutonium, which I proudly point out is the element in the periodic table named after the planet Pluto. That device produces about 200 watts to run everything on the spacecraft. That's basically 3 light bulbs. These are the 7 scientific instruments. Let me tell you what they do very quickly. Alice and Ralph, named after the honeymooners, by the way, are our main remote sensing instruments. Alice is an ultraviolet spectrometer to study the composition of Pluto's atmosphere. Ralph is a set of color cameras and black and white cameras to map the surface of Pluto and its moons. And it also has, just for grins, an infrared mapping spectrometer, meaning a composition spectrometer inside, that can simultaneously get the spectrum, that wiggly line, at 64,000 locations on a target at once. So you can just blanket the field, and you know the composition of every spot. REX is radio science, which measures the temperature and pressure in Pluto's atmosphere. Pepsi and SWAP are charged particle instruments that more or less smell or taste what's coming off Pluto's atmosphere and escaping those gases. LORRI is our long eyes. If any of you have a Celestron or a telescope at home, it's like a C8. Very high-tech one, though, with a CCD detector in the back that does our highest resolution mapping. And then we have a student-built instrument that counts micrometeoroid impacts across the solar system. The secret to New Horizons is that we wanted to fly this mission very quickly. And to do that, you have to build a small spacecraft, which we did. And then you have to buy a really big rocket. Now, when I was a boy, I wanted to grow up in the space program, and I thought a good thing to do for a hobby would be to build model rockets. And I spent all my weekends mowing lawns and washing cars to earn money to buy bigger and bigger and bigger rockets. So you have no idea how much fun it was for me to pick out the biggest rocket that anybody will ever sell you in the U.S. inventory, and to get to check the boxes to trick it out with every upgrade that they make. I'll take the most number of the solid rockets you'll sell me. I'll take the lightweight nose cone, the advanced guidance system. It was so much fun. This rocket is the size, I know it's bigger than any downtown building here. It's like a downtown building in LA. It's 70 meters tall. It weighs several million pounds. Here, if you look, that's the rocket in its hangar after it was built. Each of these solid rocket motors, there are 5, are 70 feet tall. The whole stack is 224 feet tall. That's New Horizons up top. In the payload bay, there's room to launch satellites almost the size of this room. And we put little New Horizons there it's bigger than this podium, but it's just 6 feet across. And some people were joking. They would say, New Horizons is the hood ornament on this atlas. And you can see how small it is, but look, this is not just New Horizons, that's also the 3rd stage below it. New Horizons, just the top bit. Now, before we launched New Horizons, the Tombaugh family, Clyde Tombaugh's family, came to us and said, Clyde died 8 years ago in 1997. When he died, he asked if his ashes could be sent if there was ever a mission to Pluto. Would you do that for us? And we did. And we mounted them here on that little disc inside there, Clyde's ashes. We put this inscription on it. I'll read it. Interned herein are remains of American Clyde W. Tombaugh, discoverer of Pluto in the solar system's third zone. Adele and Muron's boy, Patricia's husband, Annette and Alden's father, astronomer, teacher, punster, and friend Clyde Tombaugh, and his dates. And he was launched on New Horizons and flown all the way to the Pluto system in 2015. We made that Jupiter launch window after all those nights and weekends. We launched on the 6th day of that launch window, of a 3-week launch window, on the 19th of January 2006. And just because I like smoke and fire, I brought along a video of the launch, which I'll play. And this baby really gets up and goes because it's basically an Atlas V launching empty. I used to fly F-18s. I did that for 5 years. And this rocket does what no jet fighter can do. It takes off vertically and goes supersonic in 30 seconds. And it's the size of a downtown building. Oh, that's not right. Let's see if we can't play that video. There we go. Can we turn the sound up a little, Brad?
Go Atlas. Go Centaur.
This is Atlas Launch Control at T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond. That's 15 seconds. Everything continues to look good as the Atlas V moves and climbs away from Florida's east coast. The 5 solid rocket strap-on boosters are burning just fine, sending the New Horizons spacecraft on its way to the very edge of our solar system.
So now it's almost time for the solid rocket motors to burn out. You'll see them separate. They're staged to come off in 2 separate waves so that they don't collide with one another, which would be bad. So first you'll see, just momentarily, there go the first 2, and then 3 more. And now the vehicle shed all that weight so it can accelerate even faster on the sustainer engine. But by now it's already very high. It's above all the atmosphere. So we don't need that nose cone anymore. And just in a moment here, there it goes. There's the nose cone separating in 2 halves. So we can shed that weight. And New Horizons is now out there in the vacuum of space being shoved up to orbital speed at 18,000 miles an hour. And that's the last we ever saw of it. 8 minutes later, it was in Earth orbit. And 40 minutes after that, halfway around the Earth, we reignited the rockets to pull out of Earth orbit. And the second stage burned out. We were now escaping the Earth. The third stage lit. Solid rocket motor, very powerful, burned for 82 seconds. By the end of that, the spacecraft was pulling 14 Gs, which would kill any human being, and took us to be the fastest spacecraft ever launched, and still is. We travel so fast. You know, when I was a kid, I used to watch these Apollo missions go to the moon. 25,000 mile per hour launch, reached the moon in 3 days. Amazing, 250,000 miles, 3 days. New Horizons crossed the orbit of the moon 9 hours after it left Florida. And off we went across the solar system on a 9.5-year journey. So when I tell you how fast we were going, that we could get to the moon 250,000 miles away by that evening, you know, for the evening news, you know that we weren't dawdling. That 9.5 years took so long because the solar system is vast. We traveled 3 billion miles to reach Pluto. And we launched in January of 2006. We flew by Jupiter for a gravity assist 13 months later. By the way, the spacecraft before us to Jupiter took 4.5 years, not 13 months. The one before that took 6.5 years. And then we crossed the big gulf of the middle solar system over 2 presidential administrations, 8 years, to intercept Pluto in July of 2015. Our Jupiter flyby was very successful. Our main job was to hit the gravitational aim point that slingshots you to Pluto. If you miss that, you're going somewhere in a hurry, but not where you want to go. So that was #1 goal. But it's also, Jupiter was the only thing we passed along the way. And so this was our flight test for all of the onboard software and for the instruments. This was our practice flyby. And that went very well. And we did lots of scientific observations. As you can see, we made the cover of the Rolling Stone for geeks. And very successful Jupiter encounter. And then we left the Jupiter system and went off, as I said, on this 8-year journey, during which we shrunk the team down to just 50 people. By comparison, Voyager took 450 people to run. But with the advances in computing and automation, we could do it on a tiny team, not much more than just maybe this third or so of the room. That's the engineers, the flight controllers, the science team, the management, the budget people, everybody. And we spent those 8 years doing the work of 450 people on Voyager, planning the flyby, all the backup procedures, all the mission simulations, everything that went into it, off across the orbits of Saturn, Uranus, Neptune to intercept Pluto. I love this little video, but it always looks like we missed. We did not miss. In fact, we had very stringent navigational requirements because to study Pluto's atmosphere, we wanted to have that ultraviolet spectrometer called ALICE watch the sun set through the atmosphere as a light source and then reappear on the other side of the planet and rise so we could get the composition of the atmosphere as a function of altitude. And to do that, we had to fly through a really small window in space. We had to navigate from 3 billion miles away to a window 40 by 60 kilometers, which somebody else did the math, and I checked it, it's right. It's hitting a golf ball from here to DC and it making a hole-in-one. I know, but it's better than that. The thing is, the spacecraft is really good at a lot of things, but it's not smart like you are because it can't look at its own data. So when it takes an image, it can't tell if anything's in the field of view or not. So we have to pre-calculate with math from the orbits of all the moons and Pluto where everything's going to be, and then we instruct it based on knowing what time it is, where to point at every moment along the trajectory so that the images are nicely framed. And we do a little error analysis, and it turns out if we're off by more than 450 seconds at the end of the 9 years, the frames will be empty. Okay? So you have to fly 9.5 years and arrive within 9 minutes of the arrival time, which we did. In fact, we were only 87 seconds off target after 9.5 years. And I am very proud of the fact that we were 87 seconds early. So that all worked out, and now I'm going to show you some of the results, starting with a little family portrait of Pluto and some of its moons. So there's Pluto in the lower right, the big moon, Charon. As you move to the upper left, the big spherical thing. And then 2 of the small moons, there are 4 in total. The 2 bigger ones are called Nix and Hydra, and they're in the upper left. Now for scale, this is North America. This is the state of Texas, more or less, and these are just rocks, maybe the size of New England states. These are the 4 rocks up close, all 4 of them Styx, not named after the band. Nix, Kerberos, and Hydra, all from the mythology of Pluto. They're arranged left to right. These are the best pictures from New Horizons. Their distance from Pluto, Styx is the closest. It orbits just outside Charon's orbit, the big one. And then there's Nix, and then there's Kerberos, and then there's Hydra, the outermost. They're all just big water ice chunks. We know that because we have spectra of their surfaces. We can tell they're made of water ice. They're extremely reflective. They're as bright as fresh snow. How they remain bright, we don't know. They rotate in strange ways. There are lots of mysteries, but they are not the star of the show, and I promise to be done in an hour. So we're going to move on. I'm going to tell you a little bit about the big moon, Charon, and then we're going to talk about Pluto for the rest of this presentation. So this is a global mosaic of the close encounter hemisphere of Charon. Everything you're seeing, this entire surface, is made of water ice. But it's big. It's the size of Texas. How many of you ever driven across Texas? It's awful, isn't it? There's El Paso, and there's Beaumont. That's I-10. Yeah, it's 1,500 kilometers across that circumference, basically. And you see lots of craters, not surprisingly. Pluto and all of its moons live in this shooting gallery called the Kuiper Belt, where all these small Kuiper Belt objects are constantly raining down and making holes in the ground because they hit at high speed. If you look closely, you'll notice some craters have dark circular blankets around them called ejecta blankets. That's the stuff that's coming out of the hole in the ground. Others have a bright ejecta blanket. That's telling us that either the impactors are different from place to place or the stuff under the ground is different. We're not sure which. This big thing that I called I-10 is a Grand Canyon-like system. Geologists call it an extensional tectonic belt, which is a mouthful. What it means is that the planet split open at some point in the ancient past, probably as the water ice all froze. We know what happens when water ice freezes. It expands, and it creates these extensional stresses that got relieved by basically cracking along the equator. This vast canyon, 1,500 kilometers long, 10 times as wide and 10 times as deep as the Grand Canyon. And then one more thing about Sharon. Up at the North Pole, you have this red polar stain. We call it a polar cap, but it's unlike any other polar cap in the solar system. And we think we know how it was formed, not that we predicted it in advance, but we know that Pluto's atmosphere, which I'll show you later, is escaping to space, and Charon's in the way of some of that. And so some of those molecules of methane and nitrogen just run into Charon. And at the poles where it's coldest, they stick, they condense. And then sunlight falling on them, but unprotected, there's no ozone layer there, the solar ultraviolet makes chemistry happen and turns that methane and nitrogen into a reddish colored kind of gunk that we can create in a laboratory. And we have, and it's exactly that color. It's the same spectrum as the stuff that we see on the surface. And so we think that this whole polar cap, the whole stain, is material from Pluto's atmosphere. And if that theory is right, there should be a similar stain at the South Pole, but the way that at the time we showed up, the situation was analogous to Antarctica in the winter, where the South Pole is in darkness, but not for months like Antarctica each year, for decades in the case of Pluto. So somewhere in the 2040s, I'm going to publish a paper when we can see the South Polar Cap, and we'll see if we were right. Now, this is the binary planet, the pair itself, Pluto and Charon, and you can see how different the two are. Pluto's obviously the star of the show. It's a lot more colorful. It's a lot more geologically varied, compositionally varied. It has an atmosphere. This is one of my favorite, but not my favorite picture of the flyby. This one was taken 15 minutes after closest approach, looking back from slightly on the far side of Pluto with the sunlight filtering through the atmosphere. And there you can see Pluto's atmosphere above the very rugged surface. You can see the atmosphere as these concentric haze layers. They actually stretch up 500,000 feet to orbital altitude. Remember very early on when I was giving the beginning of this and I said the first evidence of Pluto's atmosphere showed evidence for vertical structure, and it might be due to hazes, but it couldn't tell back then, or it might be due to temperature effects. It turns out it's due to both. This is the discovery of Pluto's hazes, which were looked for decades from the ground. And it was like taking candy from a baby to see them from new horizons. It really was something. This is a mosaic created in a computer where we took images in color of the surface of Pluto and wrapped them on a sphere in a computer so that it's the appearance that you would have if you were standing 1,000 miles above Pluto like an astronaut looking down on the surface. And you can see what a rugged world it is. I'm going to show you a lot of pictures like this where there's a big picture. It's the main thing, and then there's this little picture of true color Pluto, not stretched color Pluto, with a green box, and the green box will just show you where on the planet the close-up is. So that's called a context image in the upper right. This big feature, this big white feature, is a glacier. It's the size of Texas and Oklahoma combined. It's 1 million square kilometers. We named it Sputnik Planitia, after Sputnik, the first satellite. It's surrounded by mountain ranges that tower as high as the Rockies. On every side, we think it's basically a cold trap where the nitrogen condenses in a hole in the ground formed by an impact of a small planetoid or an asteroid onto Pluto, forming this impact basin. And you can see there are lots of other interesting things going on here, like these mountain ranges that look like they were broken up, perhaps by the impact or something afterwards. These radial stress fractures, these are giant canyon systems emanating from that impact site. When we look more closely at the glacier, and this is an image made by our LORRI camera, which is not a color camera, but higher resolution. Here in the context image, you can see this is the northwest corner of the glacier against abutting the mountains. And you can see wherever the mountains stick up through the glacier to form an obstacle, because the mountains are made of water ice, which is very strong. You can see the glacier is flowing around it. Can you see the flow patterns? It's amazing. This glacier is geologically alive. Today, at 400 degrees below zero, 4 billion years after Pluto formed, there are dynamics going on. Here's another example of Pluto as geologically alive. Here in the northeastern quadrant of the glacier, up here, where these are mountain ranges, and you can see their altitudes, they're color-coded, so 5 kilometers high, it's 15,000 plus feet above the plain. You can see through this valley that some sort of ice fall took place, maybe an avalanche, tens of kilometers across, the size of the LA basin, where nitrogen ice just poured out of this valley, came down 15,000 feet. And if you look, you can't see any craters there. Craters are a proxy for age. The fact that you don't see craters means it must be very young. You know, an analogy, in our field, we can age date surfaces by counting the number of craters. And earlier this afternoon, it was raining here. If you went outside in the rain with a piece of paper, obviously the longer you left it out in the rain, the more dots, right? Same idea is true. The surface of Pluto and all of its moons are out there in the rain of the Kuiper Belt projectiles, and the older surfaces have more craters, and the younger ones have less. So, for example, here's a very old place on Pluto. You can see it's all old and beat up. It's very heavily cratered. Just a few hundred kilometers away, distance from here to LA, is this terrain, which has 0 craters on it. We've looked, we can't find one. And so, in fact, when you look across the surface of Pluto, there's a great variation. The number of yellow dots is the number of craters. Some places have craters and some places don't. Some places are old and some places are very young. And some places are middle-aged. And so Pluto, we can tell, has been geologically active across the whole 4 billion years. The oldest surfaces, in fact, do date to be as old as the planet, 4 billion years. The youngest are geologically born yesterday, only millions of years old. Nobody predicted this. Nobody thought a small planet could remain active. The conventional geophysical wisdom is that small planets would cool off pretty quickly, the same way a cup of coffee cools off much more quickly than a big vat of coffee because of the surface area to mass ratio. So we expected that Pluto would have died a long time ago geologically, but we found it's completely alive. And that was a paradigm change, that anything like that could exist in the frigid outer solar system. This is a picture of water ice mountains with methane snowcaps out in the Kuiper Belt. All those snowcaps, the bright stuff, that's methane. It's natural gas. Fortunately, there's no oxygen in Pluto's atmosphere, because if there's ever a spark or a match, the whole place would go up. But I just like this because I live in Colorado, and this picture has about the same surface area as western Colorado, and the mountains are about the same height as the Rockies. And I just think it's just cool to see basically the equivalent of mountain ranges in the Rockies out there on Pluto's surface with snowcaps. Pluto is endlessly surprising to us. This is an example where we found evidence for volcanoes on the surface. Now, these are not lava volcanoes. They're called cryovolcanoes. They put out ice. This is a big one of 3 that we found. It's about the size of Mauna Loa in Hawaii. It's 14,000 feet high. It's 150 kilometers. It's about 100 miles across. We can't find craters on its flanks either, so it is young. This big thing was built recently on Pluto's surface, just like Mauna Loa in Hawaii. And we don't understand how. Here's something else we don't understand. There appears to be nestled in the mountains, in a valley, a frozen lake. Who ordered that? We've got the composition from our composition spectrometer, Ralph. That lake surface is made of nitrogen. It's evidence that in the distant past, Pluto had a thicker atmosphere where liquids could stand and even run on Pluto's surface. So this is like that CSI game again, you know. This is evidence that something was very different in the past. So Pluto is just surprising us everywhere we look. I thought I would show, for the last thing for Pluto is this video, which we constructed from New Horizons high-resolution images, like a flyover, as if you were in an airplane, zooming over the surface of Pluto. So we're going to zoom in. Then there's a strip. We're going to start at the North Pole at the top and fly all the way down onto the nitrogen glacier. And we're flying at about 1,000 miles an hour. So this is going to go pretty quick. You can see craters on the surface. You can see the interior has structure. You can see those tracks, those linear tracks, which might be due to dust devils or tornadoes in the past. And then when you see mountains building to bigger and bigger mountain blocks, and these are large. These blocks are individually 10 to 30 or 50 kilometers across. They're thousands of feet high, and then off onto the glacier where you can see dune fields. Again, evidence of a past thicker atmosphere. And a cellular pattern, those squares and kind of octagonal shapes that are evidence that the glacier is churning due to a heat source below it. What a scientific wonderland Pluto turned out to be, beyond our wildest expectations. And now we've sent all the data back to the Earth. That took over a year. NASA just approved this last summer to go on exploring for 5 more years through 2021. And the centerpiece of that exploration is the flyby of a small Kuiper Belt object, not the size of Pluto or even the moon Charon, but more like Nix and Hydra. It's small moons. This is a building block, a representative building block, we hope, of what the planets of the Kuiper Belt were made from. We have pretty good evidence that this is a binary, so an artist named Carlos Hernandez put this cool picture together, an artist's conception of our flyby. And the flyby is on a very easy date to remember, the 1st of January, 2019. So if you don't want to go out that New Year's Eve and all that traffic and the crowds, you can spend your New Year's Eve with NASA. You can watch all this on TV, the exploration of the Kuiper Belt. It'll take place, the closest approach will take place about 9:30 at night here on the West Coast, a little after midnight on the East Coast. So we're continuing to go on and explore. The spacecraft's in very good health, lots of fuel. We're doing lots of other science beyond just this close flyby 13 and a half months from now. But I want to just close the science part of the talk by saying all those planets of the Kuiper Belt, they're as diverse as Venus and Mercury and Earth and Mars. I said they have different numbers of satellites, and some have atmospheres and some don't, and some are made of rock and some are made of ice, and they have different compositions and colors. And they're really begging for more exploration, for more missions like New Horizons to go out there and study the solar system's third zone. And I think that we'll see that in future decadal surveys, either going back to Pluto with an orbiter to do a more in-depth study, or more flybys of small planets out there. Now I want to close on a more philosophical note. This is not a stage, but a live picture when the first high-resolution image landed in our science working group meeting room on the morning of July the 15th, 2015. And these are people that worked on this project for a long time, candidly reacting to what they saw. You can feel the energy in the room. You know, to work on something like this that's a one-shot, you know, all those early missions, you know, we sent Mariner 1 and 2 to Venus because Mariner 1 didn't make it, and Mariner 2 did, thank goodness. And Mariner 3 and 4 to Mars in a pair because only Mariner 4 made it. And all those missions, Voyager, all those were always sent in pairs. New Horizons, in part to save cost, to get into that smaller cost bucket, we could only afford to send one. And if it had failed at launch or anywhere along the way, we wouldn't have got any of these goods. But we made it. We made all that work over a 15-year project. And interestingly, it was not just emotional for us. It was not just the scientific crowd. Thousands of people came to where our mission control was. This is on the morning of the flyby, and if you look very closely, you can see the countdown clock is 4 seconds to flyby. And people were just breaking out in cheers. It was like a Woodstock event, minus mud and drugs, but like a Woodstock event. And it was something you could experience on the web. We were on 500 newspaper front pages the next day on every continent of the earth. And I know that because I gave a talk like this one in 2016 in which I said, on every continent of the earth where people live. Because I thought, well, there's no newspaper in Antarctica. And the next morning, because that was on YouTube, the next morning, the editor of the only paper in Antarctica emailed a complaint and a PDF showing his front page. We did it too. It was amazing. It went so viral. NASA had 2 billion hits to our servers on our website in one 24-hour period, more than 10 times anything from any space shuttle mission, Mars landing, anything. People just love exploration. We got the Google Doodle. They wrote us into the script of Big Bang Theory. Raj was supposedly on my science team. We're showing up on magazine covers left and right. I remember my neighbor, my next door neighbor, sends me an email. I'm out in Maryland where our mission control is, and he said, Alan, you don't know this, but we take 5 magazines at our house every month. 4 have come so far. You or your mission are on every one. There's only one more. And he said, it's Cosmopolitan. If you're on the cover of that, I'm committing suicide. So we saved his life. But this really is a testament. If this one little robot out there exploring on its own could attract this kind of attention, can you imagine what it will be like in 10 years, or maybe a little longer, when 6 people set down on Mars to be the first to explore that planet? Actual people doing things like this. I think it's going to be a world unifying event. It's going to be unbelievable. It's incredible what we did just to have done it. I wake up in bed some mornings and think, did we really do that? We really did that. And I want to end with my favorite picture of the entire flyby, which is scientifically valuable, but it's just beautiful. This is true color, looking back at sunlight filtering through Pluto's atmosphere, which is actually blue, like the Earth's atmosphere. But the reason I like this picture is because the only way to get an image like this with the planet black in the shadow of itself and the atmosphere backlit by the sun is you have to be on the far side of Pluto. I worked on this from 1989 until 2016 when we got all the data to the ground. 27 years. This is my favorite picture because it can only be taken from the far side of Pluto. We did it. And so thank you very much for having me here tonight. And now we're going to take questions, right? Do we have a mic to go around the room?
No, if you could just repeat the question. So we've got a few minutes for questions if you have things to ask.
Right. So the question is, how long does it take to send a signal up there to command the spacecraft to do something? So the signal travels at the speed of light. It's a radio signal. And it's 3 billion miles. And when you do the math, that's 4.5 hours each way. Who's next? Yes. How big is the smallest planet of all those that I showed? It's a couple of 100 kilometers across.
How unstable are the objects in the Kuiper Belt? Was the Chicxulub impact crater caused by something probably out of the Kuiper Belt?
Okay, so this gentleman asked 2 questions. First, how stable are the orbits? They're very stable in the sense that they're not going anywhere. Those that are closer to Neptune or in very special orbits called resonant orbits can be destabilized, and they do leak out of the Kuiper Belt. But most of the population is still there after 4 billion years. And then you asked if the Chicxulub impact, which is the one that we believe was responsible for the extinction of the dinosaurs, could have been a Kuiper Belt impactor. Probably not. It's probably an impactor from the asteroid belt, just because it's closer. There are more impactors from the asteroid belt because they don't have so far to travel. It could have been a comet, and I don't know if there's geochemical evidence one way or the other, whether it's a comet or an asteroid, but odds are it was probably an asteroid.
Is it possible that the unexpected energy in the Sputnik glacier is somehow ultimately came from the impact that is also associated with that?
Oh, that's a really good question. He asked whether the unexpected energy that's causing the overturning in the glacier and the dynamics that we see could be leftover energy from the heat of that impact. The thing is that impact was billions of years ago, and we can calculate how long that heat would take to dissipate, and it's nothing like that long. So it's something else going on inside the planet. It's radioactive decay of materials, or it might be the freezing of a water ice ocean releasing latent heat. We're not sure, to be honest, but it's not the impact. Yeah.
You mentioned that the dunes are evidence of distant thicker atmosphere. There appeared that they were on the more recent surface of the orbit itself. So is that a contradiction?
Yeah, well, you're very perceptive. So it turns out, this is a bit of a long story. The Earth has climate cycles due to natural effects. They were discovered in the 1920s by a scientist, a Hungarian named Milankovitch. They're called Milankovitch cycles. And it's because the Earth's polar axis is tilted 23 degrees, goes back and forth a few degrees over long periods of time and can cause ice ages and so forth. Pluto has the same thing, Milankovitch cycles, but they're about 10 times bigger amplitude. And their period, which can be calculated, is 3.8 million years. So actually, Pluto has had, we believe, 1,000 cycles of a thicker atmosphere. About every 4 million years, it gets to a thick atmosphere phase. So it's not a contradiction. It was in the distant past, but it's happened again and again and again.
Do we have any idea how Pluto sorted out that that's what its diagonal orbit compared to Neptune? So if they were on the same plane, like plane record, they run into each other?
Yeah. So first I should say that the odd orbit compared to the ones like Earth's orbit is actually typical of the Kuiper Belt. And it's actually the result of simply being in the distant outer solar system. So we used to think Pluto had a weird orbit. It's only weird compared to what we know here, but out there it's perfectly normal orbit. And in fact, in other star systems, we see orbits like that in outer solar systems. So that's basically related to its location. But you ask whether Pluto and Neptune can ever collide. It turns out they're in a clockwork resonance that keeps them. Every time Neptune comes around, Pluto's on the other side of the solar system. And exactly how that came to be is above my head. But it keeps them from, and we can integrate in a computer and do the simulation for billions of years. In fact, Pluto never gets closer to Neptune than the Earth gets to Uranus, 2 billion miles, because of this resonance. That's pretty quick in getting a theory together. Okay, I hope so, because I'm sure that one's probably not right for a number of reasons. One is that there are no larger objects in the Kuiper Belt to be a moon of, and it can never have been a moon of Neptune because it never goes anywhere close. So you're going to have to show me something that's a candidate parent body for it to have orbited. Secondly, if it came off, that would not be an event that would generate a lot of energy, but the Sharon-forming impact does generate a lot of energy. So then you have to explain the Sharon-forming impact happening afterwards, and this just gets to be a rickety chain. We know that planets like Pluto formed regularly in the Kuiper Belt, so the simplest thing is it just formed on its own. It got struck in this glancing blow that created the satellite system, because all the satellites are in the same plane. And the source of the heat is a mystery.
But we also know that as star clusters form, the stars move away from each other, just as objects that form in a mass or a ring.
Yeah, that's true, but the physics is different because in the stellar clusters, the stars all roughly have the same mass. But in the Kuiper Belt, all the objects have tiny masses and can't throw each other out of the system to create the same dynamical effects. So the idea is qualitatively seductive, but the numbers won't work.
Clearly a lot of interest, but I think we're going to have to cut it off for the moment. It'd be great if you joined us for a small reception outside, but thank you very much for coming, and
Thanks. Great. Super.